Yes, I saw that there was one question that was hanging there, but I only see a question about Discord. I can answer that offline. That's fine.
I answered a couple
Good.
during the break.
All right. All right. Okay, good. Let's go.
Awesome. All right. Thanks, everyone. And feel free to keep asking questions in the Q&A. So what we were talking about right before was starting to think about the limitations of importance sampling estimators, as well as model or model-free based estimators, both of which often could have asymptotic bias. So doubly robust estimators were these ways to combine between these two different types of estimators, and particularly had this nice property that if you either had an accurate model of, say, the value function, or you could estimate the behavior policy consistently, then you could end up with consistent estimators asymptotically. So I'll try to go through some of this fairly quickly so that we have time to go through some of the later stuff. Some of the work that we were really curious about within this was to think about really focusing directly on mean squared error, so that if our goal is to make accurate estimates for the off policy setting of trying to be able to evaluate this target policy, could we try to more directly trade off between variance and bias? And what we did in this work is to both propose a weighted doubly robust estimator, which combines sort of an importance sampling estimator and a model-based estimator, and still does so in a way, well, I'll talk about the properties in a second. This often can be empirically much better. So I'll just highlight that empirically much better. It introduces a little bit of finite sample bias in return for huge gains in efficient variance, which people also are familiar with from weighted importance sampling, which I know is something I didn't get a chance to go over in depth here. The other thing we tried to do here is sort of directly kind of trade off between estimators that within a trajectory could balance between like a model-based approach versus an importance sampling-based approach. And the way we did this then is to think about these different types of estimators and try to directly estimate their bias and their variance, and then use this as a way to trade off between these different types of estimators. And I think sort of the beneficial thing of this line of work was to first show that these type of doubly robust estimators for reinforcement learning that have been proposed recently by others and then us were in fact strongly consistent, which I think is always a nice property to have, which is as our data goes to infinity, and again, I want to highlight here that we're always assuming overlap and sequential ignorability, that you would in fact converge to the real value of that policy. And again, for a lot of the domains that I'm interested in, we really care about what those actual estimates are, because often those are going to be used to make a decision about whether or not to deploy something. The other thing I want to highlight here is that there really can be a big difference in terms of data efficiency between these different methods. And I know right now we live in the age of big data, but I think that there are many domains you could consider something like, advanced stage metastatic breast cancer, where we're just not going to, fortunately, we're not going to have trillions of people with that condition. But that doesn't mean those problems aren't important. And so we're going to need statistical efficiency in order to be able to tackle some of those problems. And so what I just wanted to highlight here, even though the focus of this tutorial is really more on the theory side, is to say that if you look on the x-axis, that's the amount of data we have, the number of trajectories, and then on the y-axis is mean squared error. And this is a grid world. This is not, it's a sample toy problem. But I just want to highlight here that the approach that we proposed, which was titled Magic, was getting basically could find an equally accurate estimate with about 10% of the data. And that's important because in some of these cases, we might only have, say, 2,000 people with certain conditions, or might have small data sets. And so as we focus on statistical efficiency, that can really lead to benefits. Oh, great question. Someone just asked, how do you choose a policy such that there is overlap? Great question. Hold on to that. I'll come back to it. Super interesting question. Very important. The other thing I just want to highlight is that these types of estimators, I also had a question in the break about what do you do, empirically, you told us about a lot of different estimators, what should we do? I think things like doubly, it depends on your domain. I think for high stakes applications, doubly robust, weighted doubly robust, things that give you confidence intervals are often really important. So this is a sepsis treatment example. I believe this is from the MIMIC data set from some colleagues. This is not our work. They found in this case, so often we're going to be interested in trying to evaluate the performance of an alternative policy and see if we have confidence that it's doing better than a baseline. Phil Thomas has also done a lot of work on this. And the thing that I want to highlight here is that the estimators they looked at, the only estimator that was both a consistent off-policy estimator that could also sort of identify that there was this better policy than the physician policy was our weighted doubly robust. Now it still makes the standard assumption of no confounding, and we'll come back to that. I do want to highlight, though, that this is not always the right answer. So there's this nice paper by Lee, Valachano, and Yu, where they compare different estimators in domains that may not be as high stakes. And you are trading off robustness and efficiency, robustness sort of for efficiency. So what you can see here is fitted Q evaluation, which is this model-free estimator that we talked about before. You can see with sort of a smaller amount of data, it already is able to get closer to the true value. So if you're in cases where it doesn't, if you're not concerned about model bias so much, or if it's not as critical to be able to get a good estimate of the policy, maybe the stakes are lower, maybe it's easier to collect data. I think some of these other methods, which may have less rigorous guarantees in all cases, often, have a big benefit of being able to be very data efficient. I'll still argue that, interestingly, in one of their recent papers, this approach that we propose, MAGIC, still has state-of-the-art performance in some important settings, and I think they have a nice comparison. Both this is a nice comparison of a number of different estimators, and also Sergey Levine and colleagues have a nice recent sort of survey offline, where they also sort of think about a couple different types of methods. Theirs is more focused on the deep RL setting. I think in general, you can do a lot of blending between importance sampling and models. One thing that I did not talk about much here, which I think is really interesting, something during this semester I'm curious to explore more, is that there's this other sort of line of work from kind of econometrics and statistics that is really thinking of these things as nuisance parameters, like these model estimates or these behavior policies. What we really care about is the value of a policy. And there's been some really interesting work coming out from like Nathan Callis and his collaborator Uara and some others, thinking about sort of some different kind of, in some ways, objectives to try to compare these different types of approaches. Most of those give asymptotic style guarantees on efficiency. I want to highlight that in finite data, often the choices we make of which models we use or model-free function approximators, even if we're using doubly robust methods, that can still matter. And there's been several different papers, including from our group, that try to think about, if you really have a small amount of data, what's the best way to get those estimates. But I guess I just want to highlight too that I think that while I don't think this problem is completely closed. I feel like there's been a lot of really exciting work in this space. And I think, to me, there's sort of a lot of existing good estimators you can use for a given problem. And I think there's different ones that might be better depending on whether things are high stakes or not. But I think for many applications, we have good estimators that we could use if you care just about off-policy evaluation. I think one of the places where things are less settled is in off-policy optimization. So I'm going to sort of segue into that now. So off-policy optimization is this question of, we don't just want to look at a particular policy, we want to be selecting across policies. And one thing that I want to highlight immediately is that reinforcement learning has sort of these different ways of viewing what the process is, and we can sort of focus on, the models like the dynamics and the reward model, or we can focus on a value function, or we can focus directly on policies. And so each of these are sort of defining different types of hypothesis classes we could be searching over. And different choices might make different sense in terms of computational trade-offs or modeling trade-offs. So there's even this sort of question of, if we want to talk about finding the best, how are we defining that, and under what conditions can we talk about there being things that are the best? So the next thing here is And thanks someone for mentioning that my video feed is off. I'm turning it off mostly right now because I'm writing a lot. And so it would probably just be me as if I was giving a lecture and looking down and writing. But I'll try to turn it on when I'm answering questions. So the first thing we would do with off-policy optimization is similar to what we would do for off-policy evaluation, which is we can learn a dynamics and reward model, and then we plan. And so again, we would just have a simulator. These sorts of approaches can be very effective, and I'll talk more about them when we get to some of the sort of very recent styles of approaches. So this can be very effective. This has the same problem with kind of model bias and stuff. The second thing we can do is do fitted Q iteration, which is very similar to Q learning with a function approximator, where we have, like a Bellman equation, and we have a parameterized value function. So this is like got some sort of, this could be like a deep neural network or a linear value function or something like that. And then we want to use this, and we do repeated rounds of an approximate sort of dynamic programming style approach. There's been a lot of work on this type of approach. And I want to again give you sort of a flavor of the type of result that people have gotten for this. So I think there's a nice recent result from Chen and Zhang, where they analyze the sample complexity of fitted Q iteration. And so it says, given a data set D with a particular sample size, and I'll just note here that sometimes the sample size in terms of these kind of like state action reward next state tuples, and sometimes it's in terms of trajectories. And then the assumption that the function class satisfies completeness. And so what that means in this case is that when you do this Bellman backup, you're still in the space. So when you, again, if we think back to that nice diagram from kind of Sutton and Bartow, you had a value function here. You do your Bellman backup. In general, that may not lie in the same space. What this assumption is saying, assumption 3, is that in fact, you have a situation like this where you start in an F and you stay in F after you do the Bellman backup. And that certainly will not always be the case, but this is, that this is making that assumption that you stay inside the space. Then with high probability, after a certain number of K iterations, then the resulting value function you get, it's difference from the optimal value function, because now what we're trying to do is we're trying to find not the value of a particular policy, but the optimal policy. Is epsilon times Vmax, where Vmax is an upper bound on the value function. And so is bounded by the following. So you can say you're going to get an epsilon error times Vmax when the amount of data you have scales as the following. Now you sort of have an epsilon squared error here, like what we saw for the fitted Q evaluation. Gamma, again, is the discount factor. This is holding under some important assumptions. So this is assuming that your function space itself can contain the optimal policy. So Q star, this is your function space, like your function approximator. So Q star lies here. And then this is where we see one of the common overlap assumptions. And this type of overlap assumption, I think it was maybe originally proposed by Remy Munoz in 2003. But what this is saying here is that if it is possible under some policy to have a distribution, so let's say you follow some policy and you reach some state actions with non-zero probability, versus this is your behavior policy. So this is like the density of SA under your behavior policy. What this is saying is that that ratio is bounded. Now, for someone who hasn't looked at these quite as much, that might initially seem like a little bit of a surprising idea. But the way that I find it helpful to think about is to say, well, imagine that you had kind of a uniform density over states and actions, and you had very, very small probability in many states and actions. Then this, this kind of mu SA could be extremely small. So 1 over mu SA could be just incredibly large. And what we can see in this case is that the amount of data that we need is scaling linearly with C. And so that means that if it turns out that your sort of behavior policy doesn't cover some parts of the state action space where it would be feasible to visit that under a different policy, then your error bound might be very large. Yes, good question. So the overlap, well, yeah, the question, it's a good question. The overlap question is whether the overlap C should depend on the feature space F. Yes, to some extent. I mean, this is a really interesting point because I think if it is the case, you can always imagine kind of cheating, right? And like saying there's only a single state and then everything's in the same state, so you have perfect overlap. The problem there is that probably your Q star doesn't lie in F, and your Bellman backup error is probably also large. And so you'd have this sort of, you wouldn't have realizability and probably completeness. And so there's sort of this trade-off there between like, you could kind of cheat and make a function space which is less expressive and kind of coarser, and then it's easier to achieve overlap, but then you're sort of pushing that error into your function approximation error, because you shouldn't be able to get, like, if everything is the same single state, you're going to just have a much smaller policy class, and so you expect that optimal policy to be much smaller. But it's a great question. It is sort of there's really interesting questions over like model specification in these cases. So just in terms of what these are typically called, this sort of projection of the Bellman error, keeping you in the original function space, or keeping you in a related function space, is often called completeness. Realizability often refers to the fact that that the optimal value function itself, state action value function, lies in your space. And then this overlap assumption that's being used here is this concentratability coefficient, which comes from a line of papers from the past, and I'll have a couple of references to those later.
Emma, in this result, it seems that the function set F is finite. Is it true?
Yes, it's a good point. So I think in this case, and I don't know if Nan's on the line, I think here F does have to be finite. Probably, I suspect one can relax it just to like finite BC dimension. But I think in this case, they're assuming that there's, the cardinality of the function space that you're considering is finite.
Yeah, some sort of complexity measure of F. Could
exactly
the cardinality probably.
That's my assumption. And one of our other works, we have sort of a BC like dimension there.
Another question is, do you remember, I think none and others had a paper where they were arguing that this dependence on C is unavoidable. In a way, this shouldn't be really hard to see, right? So if you're complaining about that, you have this dependence on C in this bond, and that it seems unfortunate, we should also ask ourselves whether you can do better than this.
It's a good point. I don't remember. I think they do. I think you're correct. I'd have to go back and look at the details. I think what I would argue, and we'll get back to later, is I think in many cases, we will not have overlap or complete overlap for any possible policy. And I think in some ways, the function here is saying for any distribution that's reachable, it's not just the optimal policy. And you would hope, and we have some work and some other people have been thinking about this too, of when you have less restrictive overlap assumptions, either can you do the best possible with available data, or as long as your optimal policy is covered, is that sufficient? I also want to highlight that Nan and one of his students have a more recent, very recent, I think a couple of weeks ago, paper arguing that maybe you don't need this completeness assumption. So maybe realizability is sufficient. So this is certainly a really active area to get continued better results and less restrictive assumptions for this setting. Good question from someone. Is there some way of making sure we have enough samples from each state action pair? Randomized control trials, or if you have a small state space, often people do just sort of randomization to make sure they have coverage. I think in most realistic data sets, that's not always possible. And certainly as you start to get into continuous state spaces, then we have to make some sort of smoothness assumptions to imagine having that type of coverage. Now you could also use, so those are kind of the model-based and the model-free. Another thing we could do is do importance sampling. So importance sampling or weighted doubly Robust type methods can also be used. I mentioned before that because of the variance, taking a max over a bunch of IS estimators can be quite problematic. But on the other hand, it can depend on the setting. So these estimators tend to be particularly high variance if the horizon is long. If you have very short horizons, if you're looking at like engagement metrics or things like that, sometimes the variance isn't too bad. And I'll talk about an interesting case in this later, a couple of interesting cases. So one thing that I've been really interested in over the last few years, and as one of the potential objectives, is thinking about sort of structural risk minimization for reinforcement learning in this batch setting. And the idea being like we have all these different policy classes or value function classes or models we could use. How do we pick among them? And how do we pick among them in a way where we have some assurances in the generalization performance of the resulting policy? And so what I have been interested in, and together with some wonderful colleagues, is to think about bounds that would look something like the following, where not only would they sort of be finite sample bounds that would give us assurances on the performance of the policy before we deploy it, but that they somehow sort of intuitively should depend on like the size of the function class we're considering. And that could give us a way to start thinking about like model selection in these scenarios. So this is the type of result that I was interested in. And I think that there's been sort of a lot of limitations to, I think most prior work has not sort of achieved this. I think important sampling style bounds, which are often useful, don't typically consider the structure of the space. And I think that, you know, kernel-based methods often need samples that are exponential in the input state dimension. The fitted Q iteration bounds, some of which I just mentioned, often require this additional realizability and these bounds on like an inherent Bellman error. And the problem is that often you just don't know what your function approximation error is. So it can be hard to know what that will be. I think there's also some really interesting recent work, and there's more than I've mentioned here, kind of thinking of like some optimization techniques in primal dual. Some of those still have pretty similar dependencies or quite challenging computationally. Okay, so one thing that you might argue is to say, well, maybe it's going to be really hard to get generalization guarantees on policy performance. Maybe what we want to do is just sort of get some good in-class policy. Someone gives you a policy space, like doing policy search or policy gradient, and you just want to do this for the offline setting. And so then be able to return something that we think works pretty well. And sort of interestingly, I think of policy search and policy gradient as being probably the most successful empirical approaches for reinforcement learning. But I think there's been relatively little success on doing this direct policy optimization in the batch setting. And I think one of the challenges is that you kind of get this mismatch in state distributions, and that often can be really hard in terms of variance. And empirically, one of the papers that's been very influential sort of approached this state action distribution mismatch by just correcting for one step. So I guess before I go on for that, I will mention that I think it's a really interesting issue that like in the tabular setting, you only need to correct for one step. But when we start to think about function approximation, that doesn't always work. And so the idea that one idea is for tackling this in a paper that my student Yao Liu led, and together with some colleagues from MSR, is to leverage this sort of stationary importance sampling ratios that I mentioned before and use those inside of the policy gradient. And so the nice aspect, so now we're trying to correct not just for the difference in actions between policy, the behavior policy and the policy, our current policy and policy gradient, but we're also trying to correct for the fact that we would reach different states. And so this was the first result that we knew of that could provably converge to a local solution in the entirely batch offline setting. There's been a lot of off policy gradient work, but most of it still assumes that you're continuing to collect data. And one of the things that we found interesting here is that if you're in the fully batch setting, there was sort of less results. And the thing that I want to highlight here is that this is sort of a fairly small problem cart poll, but what you can see here is that this is the behavior policy. This is the performance of the policy you actually have data from. And again, the nice thing here you can see is that if we use that data and do policy gradient on it, we can actually sort of, there's this hidden much better policy in the data. So here, the x-axis is just the amount of policy gradient steps we've done. And so again, it's a little bit like the magic results of just, I think it's really, in many cases, being sample efficient can be really, really helpful in terms of better leveraging the existing variability in the data in order to uncover kind of these latent gem policies that might be present. So that's one thing that provides sort of a local convergence to a policy. And I think that I'll highlight here, there's some really interesting open questions too about where along policy gradients do you stop if you can't execute these policies in practice. So I just said maybe that's kind of quite far away from a structural risk minimization type objective. Maybe we can kind of get a little bit closer to that and say something like, well, maybe again, we have some class of policies. We want to compare a sort of regret measure. We want to say, you're going to do your procedure, you're going to select some policy. So we have some policy to some approach to select a policy. And I want to compare the policy you picked based on your procedure for this data versus the best thing we could have done. And again, maybe I want that error to sort of scale with some measure of the hardness of the policy. So together with Xinquan Ni and Stefan Weiger, we have the first result that I know of in this case, where it is a direct function of sort of a measure of the complexity of the class. And in terms of time, I'm not going to go through this in detail, but I'm happy to talk about it offline. But we do this for a restricted policy class. So we're doing it for what we call when to treat policies, which are like when to stop policies, but then you also get to make not just a binary decision of when to stop, but then what to do when you stop. So for example, you could imagine what type of HIV treatment do you start, and then you decide when to commence that treatment. And I think sort of the interesting thing with this is that I think it connects to the sort of econometrics and statistics communities a bit. So it leverages the idea of doubly robustness. It leverages prior work on these kind of advantage decompositions of the value function that both Susan Murphy and Shyam Kakade have developed, and says, well, what if we're doing this in the purely offline case? And then can we use some of these new ideas from econometrics to sort of estimate these things fairly efficiently? And I think, again, these sort of orthogonal and double machine learning ideas could be really interesting to further explore here. And Nathan Callis and others have also been thinking a lot about that. So I'll just highlight again that I think this is now a regret measure. So we're not looking at mean squared error. We're looking at what is the policy that is returned and how much, how close is that to the optimal policy that you could have returned in your set. So lower is better. And what you can see here is that our approach, not surprisingly, is at the bottom. And what you can see is that it gets sort of better and better with more data, but also it does that much faster than an IPW, which is essentially importance sampling. And you can also see that like fitted Q is kind of sort of more flat because it's going to have some fundamental bias. So even with more data, it may not continue to get better. So again, I just want to highlight that this sort of double machine learning and efficiency area is a really interesting area for future work. All right, I'm going to pause there for a second and see if there are any questions, but that kind of brings us through kind of up to a lot of the current work. I haven't included everything over the last year, and some of that I'll reference in the next part, of the types of techniques that people have been looking at for evaluation and optimization. And I think the optimization area has had a huge amount of algorithmic work, much of which has had really nice empirical successes. But I think our understanding of the theory there is much in much earlier stages.
So Emma, in the slide you had realizability and completeness, you said that some very recent preprints suggest that completeness may not be needed. What do you mean may not be needed? Could you elaborate?
I have not, so thanks so much for the question. I'll redirect that to Nan. I have not went through the paper really recently, or I have not read through the paper, but I had heard from Nan and one of my colleagues that they had recently added that new work. So I'm excited to read it.
I see, thanks.
All right, well, if there's other questions, feel free to ask. So let's just sort of return to kind of what the overview was. We've sort of talked about tasks, assumptions, and evaluation criteria. And what I want to do with the last part of our time is to say, let's think about some of those assumptions and evaluation criteria, and both whether or not those are reasonable and what we can do when some of those might be violated, as well as, should we be hopeful about being able to kind of leverage existing variability in data and actually uncover things that are better. So again, I said sort of these standard assumptions of kind of overlap and no confounding or sequential ignorability are very common. I'll start up and just sort of again illustrate what overlap means, because I find that really helpful intuitively. So imagine that we have a case where we just have sort of a bandit setting, and we have three different, we can think of our three arms as being like antibiotics, mechanical ventilation, and vasopressors. And in our behavior policy, or in the policy we want to evaluate, maybe we give mechanical ventilation more, a little bit less antibiotics and vasopressors. And imagine that in the data that was used to gather the behavior data, the antibiotics were given a lot more, mechanical ventilation was similar, and vasopressor was similar too, but both of those second a little bit less. So you can imagine that we would have seen all three actions. It would be completely reasonable for us to use this data to evaluate the desired policy. But it could be that nobody ever gives vasopressors to people in this state. It might be too risky. It might be that there are other complications. And so there essentially we just don't have overlap. Like we can't evaluate the performance of the policy we want to evaluate, this one, because we've never tried vasopressors. So we just don't know how well they do. Now I feel like when we look at it this way, maybe it sounds super obvious that overlap would be violated, and of course you couldn't use that. But I think in reality, this problem is often much more subtle because of this problem that we don't often have a model for how decisions were made in the data. So it may be really hard to get that sort of underlying knowledge that, oh yes, no emergency care physician would ever prescribe this here because blah, 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 and so when we don't have some of that domain knowledge, much of which might be implicit, then we may think sort of we have overlap when we don't. Now, there's actually, well, first of all, I'd say there's a lot of work historically which has assumed overlap. This is almost always assumed. But I think in many cases, many observational data settings, it won't necessarily be true. And I also think that a lot of real data sets won't necessarily have complete random exploration, but they may have some variability that we could hope to leverage in order to get better policies. So why is this bad? So, there are a lot of assumptions. I've said that sometimes you can sort of ignore model bias, maybe sometimes assuming things are Markov when they're not isn't that bad. The problem with assuming overlap when it's not is that often the things like importance sampling require overlap. And people use importance sampling estimators as if they're giving a real unbiased estimator of the policy, and that you can often get confidence intervals over those. And so when people think that you have an estimator that is highly reliable, it's really giving you a lower bound, if you don't have overlap, it can be really misleading. And so let me just give sort of a hypothetical example. You can imagine there might be some scenarios under which you would never give a certain medication to some people that are very sick. And a lot of those patients might have, really bad outcomes, kind of regardless of what you do, because they're already really sick. Well, you don't want your kind of policy optimization technique to be able to sort of cheat by just not having overlap in those cases and giving out other actions also you would never do for those very sick patients, which are never taken, because that could basically make you overconfident in the policy that you have. Whereas if you really deployed it when you got to those really sick patient care and you're making these recommendations, they actually might be much worse than what people were doing before. So these things can be really challenging when we sort of assume there's overlap when there's not. So one way we've been sort of thinking about it, and I think a number of people over the last couple of years have been thinking about this problem of sort of over-optimism, which often can be caused by lack of overlap, is what we've been sort of centering towards as a different objective is, well, what's the best we can do with what we've got? So if we imagine that there's some data distribution that you have access to, what we'd like to be able to do is try to find the best policy that is covered or that has overlap with your behavior policy. And I think this gets to one of the questions that was raised before of what can we do with the data that we have, or what if you don't have full overlap? And the idea that we had is a pretty simple one, which is to be pessimistic for parts of the state action space where you have insufficient overlap. Now, this algorithm that we have in submission right now is a model-free algorithm. And I'll talk more about some other approaches in just a second. I do want to highlight that most of the recent work that's been trying to tackle this problem has also been model-free, but a number of them have some limitations. So we won't go through it in detail now due to time, but we can come up with sort of a couple small toy MDPs, which I always find really illustrative when I'm trying to understand a problem, that illustrate why some of the previous approaches, even though they're aiming to be more conservative, that they can still be overly optimistic in some of these settings. And that also includes things like BEAR and BCQ and some of these other ones that are have been really targeted towards deep reinforcement learning in the offline case and trying to be more conservative due to sort of over optimism bias that can happen in part due to lack of overlap. And the key idea that we had is to say, well, imagine that you could sort of estimate your state action distribution that's covered in your data. And you sort of have a simple filter about whether or not you have sufficient coverage or not. And then when you're doing Bellman backups, you're only allowed to do sort of Bellman backups over parts of the space that has sufficient overlap. And outside of that, you end up sort of inserting a pessimistic bias. And one of the nice things here is that the bounds that we get end up being sort of the best with respect to the policy that is within the sort of supported set, which I think in these cases is really the best you could hope for, because you aren't necessarily, I'm not saying our bounds are the tightest, but I think this type of objective is helpful to think about, because it's saying like, if you have a good policy within the data that you've collected so far, you would like to be able to recover it. And so can we talk about how close you are to that? And if that's an optimal policy, that's great. But if it's just a really good policy, then that's also helpful. And that allows us to avoid the strong concentratability assumptions that have been made before. In some ways, we can think of it as, instead of just requiring concentratability and overlap, we're saying you are only going to search over a policy space that maintains sufficient overlap. And one of the nice things here is that on sort of an empirical side is, again, we can find things that kind of are more safe when they're generalizing. And so when you actually deploy them, on the x-axis here is actual sort of rewards if you were to run this. So this is if you were to deploy it in the real environment, that by being sort of more conservative, you get things that are more solid. And then when you deploy them, you actually get better performance. Okay, so this is model-free approaches. And I think some of the theory here is nice. But that was, I want to highlight here of like, well, why be model-free? Maybe being using a model might be better. And I think there's been some really beautiful work over the last couple of years by people showing where models can be provably better than being model-free in the online setting for reinforcement learning. And so given these sorts of results, you might wonder, hey, if this is what's happening for online learning, then maybe there are cases where provably model-based approaches are better in the offline case. And you might imagine if you have strong parametric assumptions of the models, that would almost definitely be true, but maybe it's true in some sort of general sense. And so there's been several different papers concurrent to ours. I think all of these have come out this summer on arXiv that are thinking about doing a very similar type of idea to what we were doing in model-free in a model-based way. And essentially in these approaches, this is sort of at a high level, they're learning dynamics models and they're trying to estimate the uncertainty over those dynamics models. And then they penalize parts of the state action space where those model uncertainty is high. And so for those of you that are familiar with like the upper competence-based optimism, this is exactly flipping that. And so instead of being optimistic under uncertainty, we're going to be pessimistic under uncertainty. And then we can inject that into our planning algorithms so that the resulting value function and policies we compute should be conservative and therefore avoid parts of the state space where we may have very little overlap. And empirically, some of these have really, really promising results on sort of the D4RL benchmark tasks. I think that there's still even further room to do more theoretical analyses and to better characterize where the model-based approach is good or bad and what type of finite sample guarantees might they have, analogous to some of our finite sample guarantees. But I think in general, these types of approaches are very promising. I don't think the question of how to best behave with sort of limited data coverage is solved yet. And I also think that both our method and these methods, they're all sensitive to misspecification. If you've got the function approximator class wrong, that will directly lead to error or regret. or might, right? You might have the function class wrong, but you might still be able to represent the optimal policy. So I think those sorts of questions are still very much open. Okay, so the next thing I'm going to talk about is, so that sort of talks about a line of different types of works that are thinking about this overlap assumption. And the next thing I wanted to talk about a little bit of is sequential ignorability. So again, just to go back, in sequential ignorability, we assume that all state variables that we use to inform treatment decisions are known or recorded in the data. But in observational data, this might, particularly if the behavior policy is known, this might be violated. So you can imagine when you talk to your doctor, you may have a long conversation. You may tell them that, like, you know, you've recently quit smoking, or you've lost your job, or like there's different stressful situations, or maybe you come in and you look like you've just come from a run, so they know that you're exercising a lot, or, you know, there might be different things that are providing additional sources of information that the doctor is using to help inform and diagnose your condition and make treatment recommendations. And so if there are these, and those variables may or may not be recorded directly in the electronic medical record system. Now, my personal belief is that many of those variables, at least in the US, might be recorded because, for better or worse, there's a very strong suing culture in parts of America. And that means that you have to be able to be prepared for potential lawsuits if one makes bad decisions. And so an implication of that is, I think, that the documentation burden is probably pretty high to be able to justify decisions retroactively. And there are good things and bad things about that, but I think that what that means empirically is that probably inside of the written notes that doctors make, there's probably a lot of these sort of variables that are being recorded. But in the standard sort of electronic medical record systems that are already sort of coded and made quantitative, some of that stuff may be missing. In fact, I think a lot of it is missing. And so this problem may be something that goes away a little bit as we start to get better natural language processing of those notes. But I think there are many situations where this kind of unobserved confounding can, again, be sort of interfering with the data quality and can mean that if we assume that, you know, the physician was always giving these type of recommendations, that in fact, they might not have been. They might have only be giving this to like young pregnant women, and, you know, men over 70 were getting something totally different. Now, age and gender are things we'd probably see, but there might be other factors in there they're being used that are not being recorded, and again, can lead to erroneous inference. So this is something that I think there's been, again, growing interest of. There's some really nice historical work on this from sort of the statistics and biostats and epidemiology community. Within the AI community, people like Judea Pearl and Berenbaum, and a number of others have been thinking about the problems of confounding and latent variables for a long time. Recently, there's been work kind of in this from the RL perspective. I think some of this work assumes that you're kind of in a POMDP and you can identify the sort of confounding over time as you get more states and observations and actions. Some of the work makes very, very minimal assumptions over what potential confounding could happen, and may simply assume that you know that everything's a probability distribution, and that can give you some useful information for bounds. And some work sort of thinks about how confounding can be have limited impact on the resulting reward variables. So one thing that we've been thinking about is a sort of a little bit orthogonal to this, but based on some work from some ideas from the single time step setting, is to think about confounding as having bounded influence on the decisions. So, for example, maybe if someone comes in and they're wearing yoga wear and like they talk a lot about exercise, maybe I push them to something that's sort of like a behavioral intervention instead of a drug intervention as a physician, perhaps, right? But you know, if they still have really high blood pressure and they have a lot of risk factors that are all fully observable, maybe it doesn't completely change my probabilities of making treatment decisions. Maybe it just nudges them a little bit. And so this type of model is known as bounded confounding. And it's been thought of for a long time, including for, you know, focused on single time step decisions, where the idea is that the amount that a hidden confounder, so this is a hidden confounder, the amount that could change which decision I make. So here's two different hidden confounders, U and U prime. the amount that this could perturb my likelihood to pick one action versus the other in terms of as a behavior policy or as a decision maker is bounded. So it can't be wildly different. So that says, whether they're wearing yoga pants and talk a lot about exercise, maybe I still mostly prescribe them, a blood pressure medication, but it slightly increases the likelihood that I would perhaps suggest some behavioral modifications. And so I think this is a really interesting model because it's sort of, in some ways, we can think of this as sensitivity analysis. It's saying like, imagine that your behavior policy is a little bit wrong, and it might be a little bit influenced, or some sort of fixed amount different than what you can kind of observe, but it's not going to be wildly different. Under those scenarios, can we still get bounds on off-policy evaluation or even off-policy optimization in a way that we think we might have some assurances? So unfortunately, even under this case, if you have this bounded confounding, if you have it for enough time steps, it can still lead to sort of an exponential uncertainty over your estimation. But one of the things that we did is showed that if you think of there being maybe a limited amount of time steps on which there's confounding, in particular, if there might just be one, for example, maybe you prescribe a policy and then that's sort of executed by people more, then we can get some scenarios where even under some limited amounts of confounding, you could still uncover that one policy is better than the other in terms of its value. So we looked at a couple of different simulated domains based on healthcare settings. And what you can see in these scenarios is, for example, here, this is showing you sort of how much confounding you have. And if you have a ton of confounding, then eventually you have no idea what the behavior policy is, and it's very hard to make inferences because there could be so much confounding, things could really, really change. But what we could see here is that this policy here, which is with antibiotics, that given some amount of confounding, we can still derive upper and lower bounds on the performance of the policy that tell us that it's still better than without antibiotics. And you can see that a sort of more naive approach, which could be something like just thinking about your behavior policy having some epsilon error and then kind of multiplying that for the number of time decisions that you have. And we use several different constraints in the optimization process we do, that this would sort of not make it that you can only be sure for a much smaller amount of confounding. And so again, this sort of just provides us with a way of being more robust to the failure of some of these assumptions by carefully designing the optimization process. This is work with Ramtin Karamati, Steve Yadolowski, and Hong Namkung. I think there's a lot of work to be done in terms of the unobserved confounding. I think some of the recent work that's thinking about proxy variables and places where you can identify things and more POMDP-like approaches is very promising when those assumptions hold. But I think even just thinking about when these sort of sensitivity analyses are reasonable is helpful. Sort of just two for their last few minutes, I guess I'll just say a couple quick things. One is that in terms of the evaluation criteria I've talked about so far, I talked about sort of scalar rewards and empirical accuracy, et cetera. But I think one of the really exciting things that we're moving to in reinforcement learning, and Anka talked about this a lot, is the idea of reward functions being more complex. And so I think in many cases, we care about things like risk sensitivity. We care about constraints for safety reasons. We care about constraints for fairness reasons. And in many cases, we may actually have sort of a Pareto front of different objectives that we care about. And particularly in the batch RL setting, that we have this opportunity to sort of show how different policies would compare across this space. So I think that that's a really interesting direction for considering in the batch RL setting. The final thing I want to just end with is whether we should be hopeful. So I think there's been a lot of really amazing successes about imitation learning. And in some ways, batch RL is imitation learning in the sense that we're both assuming often that you have sort of this amount of data to start with. And you could hope to imitate the best policy in that data, or imitate the policy that was used to generate that data, like in imitation learning. Or what we're hoping to do is something actually more ambitious, which is to outperform the behavior policy. So essentially, we'd like to say, we've got this old data. Can we only just match pi b, or can we do better? So I just want to give you two reasons to be optimistic. The first is the way I first got interested in this problem, which is through my work on a fractions game, where kids manipulate spaceships to try to learn about fractions. And the policies here are like, what sort of activities do they get at which time point? And what we had in this case is we had a lot of prior data and we wanted to learn this new policy. And the interesting thing in this case is that by doing reinforcement learning, we could actually learn a policy offline that increased student persistence by 30%. And it was also 30% better, both than random and better than sort of the expert policy from before. That sort of illustrates why in some cases there might be a lot of things left on the table when you do have quite random data. But I think even more optimistic than that is some really nice, very recent work that just came out in AI Stats about a week ago from Finale Joshi Velez and Joe Futuma and Michael Hughes. And here it's just observational data. I believe this is from the MIMIC data set, and they're looking at hypertension. And they had a really interesting approach here where they're sort of doing this model-based, a POMDP model-based approach. So that's kind of the policy class they're considering, but they're using an estimator to compare amongst those policies that makes very little assumptions. It's an important, an important sampling approach estimator. And they also have some other really interesting things here about interpretability. But the key thing that I just want to mention is sort of the take home, which is if you look at sort of the actual performance of the policy, so this is like the policy in the real data set, you can see that they're able to find both value function methods and their method can find something that looks substantially better than the policy that's being used for patients right now. And so when I saw that, I thought that was really optimistic because it seemed like, and you can see here, it's not just, you can also get confidence intervals over these type of estimates as well. But I think that it's really great to see cases where there is sort of natural variability in the data that we have access to that we could leverage in order to get much better policies, even if it isn't feasible for us to actually run online experiments. And so with that, I'll conclude. I think that to me, one of the big challenges that we all face when we're trying to figure out our research directions is, do we want to do things that we think are more applied and towards problems that we care deeply about? For me, those are things like education, healthcare, and versus some really incredible, beautiful theory and new types of algorithms. And one of the things that I think is so exciting about the batch offline RL setting is that it's exactly at this nexus of the two, where there are so many applications that could really benefit from it. And there's so many important open questions that we still need to tackle. So with that, I'll conclude.
Thanks. Do you have some questions? So yeah, you talked a lot about this overlap and the lack of overlap, or what can you do? Do we have any lower bounds for this setting? So I imagine that you collect some data, there is some underlying MVP, maybe you're making assumptions that data really comes from MVP and whatnot. And then you can ask the question, given this data, how well can an algorithm do? And what sort of algorithms would achieve that lower bound? But it has to be a non-uniform lower bound, right? Because otherwise the overlap is going to come in and whatnot, right? So here the overlap usually refers to how much overlap there is between the distribution induced by the policy you're shooting for to estimate its value, or like discover versus the distribution that was generating the data.
Or normally it's even worse than that. It's like,
is a free variable, right? Like you're choosing the policy. So do you have a sense of this? So you quickly show the result of a new paper that is under submission. Is that paper out? Yeah.
For us, yeah, it's on archive. For the one we have for model, okay. It's a model-free approach. I think the model-based ones empirically have very nice performance, but I think the model-free ones, there's some nice theory there. I think I don't think we know that yet. I think it's a good question. I think the original concentration and overlap assumptions were really quite strong because it was not just about the policy, the final policy that you care about, but you sort of had to have coverage for any distribution you might be any distribution you might be able to sort of reach under any policy. And I think part of the reason for that is you're doing sort of a series of dynamic programming style backups. And so for each of those policies, they need to be covered. And so you might have to sort of support many policies outside of the one that you care about at the end. And if you just knew the one at the end, then importance sampling would have that covered, even if a dynamic programming method would go through some policies that weren't. But I think, I don't think we know about sort of lower bounds in terms of what are the best results in terms of overlap we could hope to expect. Again, based on your prior conversation, I'll look back at Nan's paper from a year ago to see the lower bounds there. My guess is that the lower bounds will be pretty awful, that you could construct sort of awful MDPs where there's like one really great state, and if you don't, even something like a chain type MDP, it's very hard, particularly under like uniform policy, to see those high rewards, and that's where you need to spend time.
But maybe you should aim for an instance-dependent lower bound and instance adaptivity, because otherwise, maybe as you say, everything is going to be just look very, very dark. I think.
Yeah. And Dylan just brought up a point saying that he thinks that Nan's paper mostly shows it's qualitatively required, but it doesn't say that the particular functional dependence that we see right now of the overlap inside of the bounds is needed, or if there might not be other better alternative definitions of overlap that might be preferable.
I read maybe you didn't see that because obviously you were speaking, but there were some questions related to this in the chat. And I pointed people to a recent paper by Mengdi and Yaki Duan, student of Mengdi. They're talking about off-policy for linear function approximation. It's just policy evaluation, but like you see part of these issues there. And they point out that it's basically about the underlying covariance matrix, not really about overlap per se. So that kind of what happens if you have functional approximation. And the nice thing is that they have minimax optimality design, so they have lower bounds and upper bounds that show that the quantities that appear in their bounds really have to be there. But again, this is worst case. And when I'm seeing these optimistic results, then clearly those happen because we are not in a worst case scenario. But maybe there is a way of understanding how far you can push results on an instance by instance basis. So you might require that the algorithm in the worst case is pretty good, and amongst all those algorithms you can ask like how well any algorithm that does pretty well in the worst case can do on a particular instance. So this way you're restricting the set of algorithms so you don't arrive at vacuous results. And then you can ask like, okay, how complicated is an instance for an algorithm that is near worst case optimal? And then I would think that it should be possible to answer these questions. But yeah, I don't know the answers to this. Okay.
Yeah, something I haven't read that paper by Maggie and her student. My guess there is that, like the model-based and the model-free methods that I mentioned, it will still require assumptions on realizability and sort of lack of bottom specification, which I think that empirically, I think that's a big deal for a lot of the applications that that we could hope to use BatchRL for.
No, how serious the assumptions are. I mean, like if you allow this blow up of the approximation error by a factor of square root of d, then it seems that realizability is not such a big deal. I mean, okay, maybe square root of d is a big deal, but that's the best that you can do in general. But I don't think that in a nutshell that realizability would be a showstopper. I think that those are just initial results that people are going to extend these to the unrealizable setting.
Yeah, I think it'll get tighter. I mean, I think some of the bounds that we have right now for lack of realizability ends up essentially having constant terms or and I think for many of the cases that I personally am most interested in, like we really need finite sample guarantees of an accurate lower bound before we would make a decision about whether to deploy something. And so like constants matter in those cases, or having sort of estimates that we think are very solid. And so I don't I don't think the theoretical work in the model-free and the model-based approaches have come to that part yet. If one's in a setting where it's not quite as high stakes, I think it's completely reasonable. But I agree with you that maybe the bounds will get much tighter. And I think a lot of this, there's been so much work in the last year or two that I suspect people may be even working on it now.
Okay.
And were you referring to a discussion in Discord? Yeah, I wasn't monitoring that during my talk, but I'll look it up later.
So on the Discord, we try to answer all the questions that came up, and I don't really see any open questions. I think that the open question that was left unanswered after the first talk was overall, what's your intuition of what to use when? But I guess at the beginning of this talk, you try to answer that a little bit.
Yeah, and if anybody has follow-up questions, feel free to send me an email, or I'll be on Discord and others too.
So I have a question about ignorability. I'm always struggling to understand this notation, and I have to reread all the definitions and everything every time. But at one point, I decided that ignorability is this assumption that you have to record everything that the decisions that you want to argue about in the future are based on in your data set. And if you did that, then you're fine. And the ignorability is just like some formal description of this. Is this
Yeah,
correct?
That's how I think of it. Yeah, that like all of the information you'd ever need to categorize why decisions are made now or for the rest of your trajectory are captured.
Okay, then it doesn't matter whether you're in an MVP or PAM-BP or whatnot. It is just that there shouldn't be any hidden information that was used and that could be correlated with the outcome in some sneaky way that you don't know about, right?
Yes, and I guess that's an important distinction, that it has to, it's affecting future actions or future states or future rewards. Those are the things we care about.
I guess the assumption that I remember is a little bit stronger than ignorability, because maybe there is some information that you can ignore because that information is not impacting the future outcome. So then, like, why care? But in general, it's really hard to know. So it's, if you want to be safe, then you should just include all the information that is impacting the decision variables that you want to reason about in the future, right? Okay.
Yeah, yeah.
Okay. Okay. All right. Okay.
All right. Thanks, everybody. See you tomorrow.
Yeah. See you soon. I think in half an hour. Next talk.
Oh, yeah. Next talk. Thanks.
Bye.